In this video, we're going to show you how to monitor the DisplayPort auxiliary channel. We're going to monitor link training transactions between a source and a sink. So at the generator, we first have to select the interface. In this case, only the DisplayPort interface is available. We can also choose a format and an image, so we'll go ahead and select any suitable format here. Just select something there. You get the source key to do that, and then hit the blue button associated with the format. Okay, then we go to the content key, and we can scroll down to any sort of test pattern. It doesn't really matter. We'll just choose a standard pattern such as SMPTE bar. You see that we're scrolling with the arrow keys and then pressing the blue button to get to SMPTE bar. So now we've got that set up, we can make our physical connections. So we have our DisplayPort source and sink, and we have our generator here. And essentially what we'll be doing on the 882E, we have the DisplayPort transmitter and the DisplayPort receiver, but we also have, with the receiver, the auxiliary channel analyzer inputs. And we're going to be monitoring the transaction between the source and the sink then. Now, in order to make that happen, we'll disconnect a cable from the generator to initiate a hot plug that causes the cascade of auxiliary channel transactions for link training, as well as the EDID read and so forth. So we'll take the cable from the source and the display. We already have them connected up to the devices. And we just have to connect them to the auxiliary channel analyzer inputs. The DisplayPort TX and RX emulated ports on the 882E are not used in this case. So let's turn around and take a look. And we'll plug the source into the appropriate port on the auxiliary channel analyzer, and you see the transmit and receive ports are not used. Let's plug the source in there and plug the display into the auxiliary channel analyzer port labeled to sink. Okay, so we have our connections. Now we can go, and you see an image coming up there because the source is being passed directly to the display in this case. So now we're ready to go to the auxiliary channel analyzer and monitor the traces. So we're at the PC now, and we can go connect up to the web page, type in the IP address, and then go to open up the auxiliary channel analyzer application. And we have to make sure we select the connect to the generator and select the DisplayPort port, and then hit capture. Now we can go to the generator and do a hot plug. And when we do that, we see the traces being logged and shown in the auxiliary channel analyzer. Okay, we're going to show you how to review and examine the traces taken from the ACA. These are aux channel traces. These could be I2C emulation reads for the EDID. They could be native aux channel reads and writes for the HDCP or link training. So if you look at the ACA here, you have on the leftmost column, you have a number. Each record, each logged record has a numerical indicator, an integer. And then you have the time since boot shown here. It's a real-time snapshot of when each record occurred. You have delta time here, which allows you to highlight any line. Hit delta mode over here on the upper right. And then you will notice that all the times for all the records are shown in terms of how long they were preceding or succeeding that reference record. So in this case, 12 milliseconds Record 7 occurred 7 milliseconds after record 6. I'm going to go back to the regular mode, the cumulative mode, and we'll look at some of the other fields in the auxiliary channel analyzer. Master slave, this is what direction the transmissions are going. And what this means is that when there's a read request, that'll show up as master to slave, and the reply will be slave to master. If there is a write, that will show up master to slave as well, and then slave to master on the acknowledgement. Okay, so if we look at the way the data is logged here, let's just take an example here of a read message, a native read. This is a read of a DP CD register here, register 202. So let's go ahead and highlight that. And you see the details. There's two sections in the details. You have the data in raw hex text. Then you also have the human parsed out data parsed out in human readable terms. So this 90 is indicating that this is a read, and it's a read of a native aux channel transaction, a read of a register, and that register is shown here in these bytes 202. You see that up here. You also see that over here. The next byte indicates the number of bytes that you're going to be reading in this case. And it's always offset by 1. So you always add 1 to this value because it starts at binary 00 equaling 1, 01 equaling 2, and so forth. So this means we are reading 1 byte from register 202, and you see in the response here, we in fact have read that register, and the results are shown here. Okay, now let's look at a read transaction on the I2C, and these are going to be, in this case, these are going to be EDID related reads. So let's just take one here, and notice the I2C under the source, and it's a request to read 16 bytes from address 50. So again, we look down here and we see that in this case a read is indicated by 50, or the 5, for an I2C read. The address shown here, 50, and the number of bytes it's going to read, 16. That would be in 0F is 15 in hex, that'd be plus 1, 16. So it's reading 16 bytes. It's reading the EDID in 17 byte blocks. And you see that shown here. Okay, let's go down further and look at some writes. Actually, I see one right here. Let's look at a write of the I2C. So in this case, it's going to write to address 50. It's going to write a 0. And you see that the data 0 to 50. This 4, 0 is an indication that it is a write to the I2C, or using I2C emulation. The address is shown here, and the value is shown here. Now let's take a look at a write for a native aux channel transaction. Looks like we have one here. So we're showing a write of a value of 82 being written to register 101. So you see the data here. In this case, a write using native aux channel transactions is 80. The address 101. The number of bytes that are being written is 00 plus 1, that's 1. and the value is 82. And in this case, you see what's being written here is to DPCD address 101, the value of 82, which is an indication lane count set to 2 lanes, and whether or not enhanced frame capabilities are supported, in which case, this case it is supported. Okay. So that is a brief introduction of how you interpret the traces, kind of an overview of the ACA trace monitoring for the auxiliary channel analyzer. We're now going to go through the aux channel traces here and hit some of the high points of the EDID transactions, link training, and a little bit about HDCP. Okay, so if we look right up front here, we see some reads to these 68,000 series registers, and those are the HDCP registers. So in this case, we see a read of 5 bytes, 68,000, and then you see a reply. These are the sources reading the displays BKSV. And you see the values down here on the left. Okay. So you see the read here of 5 bytes. It's 96 or 68,000 is the address in this case. 9 indicating that it is a read. And then you see the number of bytes is the 4 plus 1. Okay, so down here we see another transaction to the 68,000 series, 882EA-DP, and you see the reply there. In this case, if you look at the details, HDCP repeater capability does support downstream connections. HDCP capable, no. And so that is why you don't see any 68,000, any more HDCP transactions going on from this point forward, because the sync reveals itself to not support HDCP. Okay. So let's go through a little further here and see what's going on in terms of the link transactions. This read right here, 16 bytes from address 0, is the reading of the DPCD receiver capability field, all 16 bytes there, and you see the response coming back. And it's all parsed out here. You see the receiver is support 2.7 gigabits per second per lane, and it does support 4 lanes, and there's some other data as well. Okay, so we can also look and see, let's see if there's anything else interesting here. Here we're reading, looks like it's reading 2 bytes from address 100 and getting a response, and it's just, in this case, reading the link configuration field. And again, it's 2.7, but now it's shown to be two lanes. And you'll see that that is what the source is going to use during the link training, 2 lanes. Okay, so let's go down a little further. Now we start to see a lot of I2C transactions. These are the EDID reads. So if we look at one of those, we see a read of 16 bytes at address 50. Again, the 50 is an indication of a read of a I2C. 50 is the address, 15 plus 1, 16 bytes. And then you see the values in the next line being shown here in hex. And you'll see a lot of EDID reads, and interspersed within that are some native reads, some aux channel link layer chatter. It looks like, if we go down a little further here, we see that the final EDID block of 16 bytes is read here. And that appears to be the end of the EDID reads. Okay. So now we're going to get into some of the link training and some of the setup for the link training. So if we look here at this register, it's reading 1 byte from address 1, and it's finding out that the display supports 2.7 gigahertz per second, gigabits per second per lane. And then it's also reading register 2 and finds out it supports 4 lanes. Okay. Go down a little further here. Now you see some writes to the 100 register, which is the link configuration fields. And you see that it's writing that it's going to use in the link training 2.7 gigabits per second per lane. And it writes 1 byte to 101, where it says it's going to use 2 lanes. So it's writing to the link configuration field as part of the setup for link training to inform the receiver it's going to use 2 lanes. Okay. Now the first phase of link training is the clock recovery phase. And if we look, that should begin here right away. And you see that that should be, the beginning should be a write to indicate training pattern 1 is going to be used. And then there are some other reads and so forth here of the adjust request lane, indicating that it's going to be, or should be using, or being instructed to use the pre-emphasis level of 3. And we see some other transactions looping around in the first phase of link training clock recovery. And we finally see here 290 that when 1 byte is read to 202, record 290, we see that the lane 0 and lane 1 clock recovery is set, is 1. And that's hex 1. So the clock recovery phase is in fact done at that point. Then the second phase of link training is the channel equalization. So that should start soon after that. First phase is completed. So here you see a read of some registers. And this 297 line appears to be where the second phase begins. And you see it looping through here using different values of equalization, or pre-emphasis, I should say. And I'm not going to go through all those in detail, but I'm just going to go down and look for where it looks like the channel equalization and symbol lock phase is completed. And that appears to be, let's see, this could be it here. Reading 1 byte from 202. Yes, you see down here 0 and lane 1, clock recovery, channel equalization, symbol lock are all set. It reads it one more time, apparently for good measure. And you see it's still set. And then the whole process culminates in the source writing to the display at register 102 that link training is no longer in progress, meaning it's done. So that is a quick tour of the transactions, in this case between, always a case between a source and a display, showing the EDID reads and the HDCP and the link training.